Okay, let everybody into the room. Okay, welcome to Wednesday, September 30. And we're in the middle of discussing circular functions, and we're going to continue to do that today. So this is the big theme today. Thinking of sine theta, cosine theta, tangent theta, and the reciprocals, cosecant theta, secant theta, and cotangent theta. As the so-called circular functions. So that's the theme. And that's why I want this drawing that we used last time. And in case I want to reproduce it, I want my Quaker Oats top. And I'll set those aside for the moment while we get ready to go. Make sure I have power to my camera here so that the battery doesn't run out. Okay. It's a little bit gray outside today, but you can still put on a sweater and take a walk afterwards. I did revise our formula sheet, and let's start by showing you that. So I'm going to go to my website, share my website page with you. We're in week 5 right here under handouts. It says still fundamental trigonometry identities, but I added a lot of identities to that. Let's get some people in the room here. So let me show you, and you might want to print out this trig identity worksheet now that it's been revised. I can put it on the camera, but it'd be easier for you to see on the screen. I definitely have internet lagging issues myself here. So bring it up that way. You know, I could bring it up another way, and I keep forgetting about that. So let me bring this just up as a document on my computer screen. And then I can share the document on my computer screen. If the document on the website hasn't come up. So I'll ditch that and share this document from my computer screen. Okay, so I am, okay, give me a second here because I thought I was sharing that document and then the document disappeared. Okay. Okay, excuse me. So I was not on the right screen for that document. This is the revised fundamental trig identities worksheet, formula sheet, whatever you want to call it that I gave you. It has everything that we had before: trigonometric functions, correct picture, reciprocal identities, quotient identities. But now we've got these tips for calculating in radians. And today we'll talk about these 3 formulas down here: arc length, angular speed, and the area of a sector of a circle. Cofunction identities we previously had, the Pythagorean identities we previously had. Always pay attention to the quadrants in which the trig functions are positive and negative. So in quadrant 1 and 2, sine and cosine are positive. In quadrant 3 and 4, sine and cosine are negative. I tried to indicate this with these little circle arcs right here. Different colors if you see the colors. Pythagorean identities. Now, other than that, I've got a lot of identities you haven't seen yet. Sum and difference, double angle, half angle. And then on to page 2, a lot more identities. So now that we're rolling in the course, almost finished with 5 weeks, what I did is just added all the rest of the identities for the rest of the course. So this formula sheet is good for everything we're going to do in the whole course. If you haven't seen these identities yet, or we haven't done them, don't worry about them. We're not going to use them. But we will. The reason I'm showing you this is talk about the even and odd identities today. So that's why I wanted to show you that handout. So you can print that handout, keep it handy in your desk when you're working. Probably better than bookmarking it online if the internet is slow or something like that. So let's get out of there. Let's go back to my picture. I'm looking at that. Okay. Do you remember the day that we said to you a 45, 45, 90 triangle has the side ratios of root 2, 1, and 1? And the reason we said that is because if you let this 2 legs be 1, then 1 squared plus 1 squared is equal to 2. But that's equal to the hypotenuse, or the c squared. A squared plus b squared equals c squared, the Pythagorean theorem. And so that's how you decided that in a 45, 45, 90 triangle, the hypotenuse can be represented by root 2 if the legs are 1 and 1. But then I also said to you at that time that sometimes it's more convenient to think of the hypotenuse as being the 1. I want to recall this in your mind right now. That doesn't mean I don't know these two sides. I could use the Pythagorean theorem again, or I could just use the instructions in this triangle. To go from B to C, I multiplied by root 2. But I can also read this triangle like this. To go from C to B, I divided by root 2. So if I said that the hypotenuse was 1, if that suited my purpose, that the hypotenuse should be 1, I am not in the dark about these 2 legs. I will just divide 1 by root 2. And now I want to show you another coincidence. Remember, we call this the hypotenuse. If this is the angle theta, which is 45 degrees here, this is called the adjacent side, and this is called the opposite side. Normally, we say the sine of theta is opposite over hypotenuse. And in this problem, in this triangle, that means the sine of 45 degrees is opposite over hypotenuse, 1 over root 2 divided by 1. But because of the way we chose the hypotenuse, choosing the hypotenuse equal to 1 makes this division, kind of overwriting. Anything divided by 1 is itself. So the sine of 45 degrees is actually 1 over root 2. Now you know that the sine of 45 degrees is equal to 1 over root 2 on your calculator, on your exact value sheet, in any number of ways. But the reason why I'm pointing this out right now is it's very, very convenient to make the hypotenuse of a right triangle 1 unit long. Because then all the formulas, like cosine theta equals opposite over hypotenuse. Sorry, cosine theta equals adjacent over hypotenuse. Anytime I use hypotenuse in one of these formulas, all I have to do is write 1. In fact, in a sense, all I have to do is not write it. The cosine is just the adjacent side over 1, which is the adjacent side. The cosine of 45 degrees is 1 over root 2. So now to make our point today, and this is what I'm going to show you, I'm going to talk to you about the magic of always making the hypotenuse 1. And I gave an example here in this circle yesterday that we'll come back to. If I have a 60-degree angle and the hypotenuse is 1 unit long, then I know how to get the short side. Short side in a 30, 60, 90 is always 1/2 of the hypotenuse. So that makes the short side 1/2. And the long side, root 3 over 2. But relative to this angle, which is 60 degrees, that also tells me that the cosine of 60 degrees is root 3 over 2. Because cosine, sorry, getting ahead of myself. The cosine of 60 degrees is 1 over 2. Because cosine is adjacent over hypotenuse, and if the hypotenuse is 1, I just have to read this number as the cosine. Same thing with the sine. The sine of 60 degrees is opposite over hypotenuse, root 3 over 2 divided by 1. That's just root 3 over 2. Now think about that point, over 1/2 up root 3 over 2. That is the ordered pair that intersects this circle. So let's put it all together. On the unit circle, on a circle of radius 1, the angle intersects at this point, and the 2 coordinates of that point are always cosine of theta and the sine of theta, whatever that angle theta is. And I'm going to pull this up, not on my website because I don't want to deal with that delay here, but I have a handout on the website called the unit circle. And if I shared this handout with you right now, just on my computer screen, and I shrunk it down a bit so we can kind of see it equally. That is the purpose of this handout called the unit circle. If I pretend that I'm on a circle of radius 1, so over here on the positive x-axis, this is 1, 0. Austin is bringing an interesting note. The file is in your trash. Not sure exactly what that means. I am going to investigate that. That is the way somehow Google is collecting my files up there. If you see that idea again, the file is in your trash, let me know for the formula sheet. So technically, I'm going to run over here and check this. The file shouldn't be in the trash, but I could have made an error. Got it, got it, got it. Google Drive. That's 121. Handouts. Oh, okay. I can understand. I can answer your question, Austin. So my file is up there, and this is kind of funny. It is the way Google Drive operates. Let me check that, and then I'll answer your question. Got it, got it. Got it, got it. Handouts. Fundamental trig identities. Austin, what happened to you? And no, this is really important because people are having those issues. What happened to you is you either did one of two things. You might have bookmarked the formula sheet, which you probably didn't do. But this is what happened. When I put up the new copy of the formula sheet, I threw the old one in the Google Drive trash. But your browser was holding on to the old one or holding on to the path to the old one. And that's what the browser calls caching. When the browser keeps old documents that you visited handy. So what is happening there is your browser went to retrieve that old document, but I had thrown it out, so it's no longer accessible to you. If you reload my web page, you should refresh your browser with the link to the new improved file. That is a weird explanation, but that's part of what is happening when I share a file with you in Google Drive. So thank you for bringing that up. Okay, back to the unit circle. I always prefer you ask me questions like that because that way I get everybody straightened out at once, get everybody on the same page at once. Let's pretend you had a circle of radius 1 centered at the origin, and that means on the right-hand side, positive x-axis, you've gone 1 step over and 0 steps up. That is 1 and 0. But with a radius 1, all these points x and y become the sine and cosine, I say right here, become the sine and cosine of that angle. X slot cosine, Y slot sine. So 1 and 0 not only stands for the name of that point on the unit circle, it also stands for the fact that the cosine of 0 degrees is 1 and the sine of the 0 degrees is 0. Look at the 45, 45, 90 triangle. The point at which the 45-degree line strikes the unit circle is 1 over root 2, 1 over 2. In decimals, it's about 0.7071, 0.7071, not quite 3/4, a little more than 2/3. But the x slot automatically represents the cosine, 1 over root 2. The y slot automatically represents the sine, 1 over root 2. Same thing for 60 degrees that we just did, or 30 degrees. What is the sine of 30 degrees? It is the y coordinate of this point, 1 over root 2. And that works for 15 degrees and 75 degrees. Notice you compare 15 degrees and 75 degrees. When I talk about 15 degrees, then the y coordinate is shorter than the x coordinate. So that's why I have the plus sign between the root 6, root 2, and the minus sign between the root 6, root 2 for the y coordinate. But the cosine of 15 degrees must be root 6 plus root 2 divided by 4. If you stand that 15, 75, 90 triangle on its short side, if you stand it tall, then that short side is now the x coordinate, or the cosine of 75 degrees, which makes the cosine of 75 degrees root 6 minus root 2 over 4. Now, just for fun, because we know we can verify anything in the calculator, and we should practice doing it. Let me just check out the cosine of 15 degrees. Turn it on, clear other work. Let's always check mode first now. From now on, we're always checking mode to make sure we're in degrees or radians, whichever one we want. So we're in degrees, so let's talk degrees. Cosine of 15 degrees. Calculators say 0.9659258, but according to our logic, that is the 1575/90 triangle, and the cosine is the x-axis. So the cosine should be the square root of 6 plus the square root of 2 divided by 4. It's the exact same number. You know, cha-ching, winning. I got the exact same number here. Now, in the NFL, when somebody scores a touchdown and they go into the crazy dance and stuff like that, you know, some players favor that, some players don't. NFL tried to ban it, right? What did the NFL say? We don't want any more end zone celebrations. Well, that lasted about how long? I think they tried that for one season. But players had another saying, and the players said, you know, act like you've been there before. So you go and score a touchdown. It's the first touchdown of your career. You're probably going crazy. Or, I don't know, basketball, baseball, softball, whatever sport you like. But after a while, you've been in the end zone a couple of times. You take it with a grain of salt. You don't go all crazy. You act like you've been there before. So I want to say that about these numbers right here. Cosine of 15 looks mysterious on the calculator. But according to those famous triangles we memorized, that number is not mysterious. That number is this beautiful root 6 plus root 2 over 4. It is the same number. I could get all excited about that, or I could just realize, wait a minute, that's what I knew was going to happen anyway. I could act like I've been there before. Okay, so let me talk about another hypotenuse of 1. And these triangles are so important. 30, 60, 90, 45, 45, 90, 15, 75, 90. Remember I told you, and Austin actually went and verified it last time, that if you want to draw a 30, 60, 90 triangle, he did it with the 15, 75, 90 triangle, that it's pretty fair to just draw 7 boxes by 4 boxes. That's within a quarter of a degree of the truth. And we learned that the ratio of sides is hypotenuse is twice short side, and long side is root 3 times short side. Long leg is root 3 times short leg. But if we rather focus on the hypotenuse as being 1, I drew them the same size for convenience, but you know, this hypotenuse is exactly 1/2 of that hypotenuse. That makes this short leg exactly 1/2 of that short leg. Remember how the sides are proportional? And that means for a 30, 60, 90 triangle, the horizontal portion, the adjacent side, over the hypotenuse, which tells us the cosine, is just root 3 over 2. If the hypotenuse is 1, then adjacent over hypotenuse is just root 3 over 2 divided by 1. Same thing for sine of 30 degrees. It will be 1/2 over 1. I won't even bother to write the over 1. I'll just say 1/2. And that will be the point on this unit circle. Root 3 over 2 over 1/2 up. That's the name of this point on the unit circle. Root 3 over 2 and 1/2 up. Now let's test it. What is the x-coordinate, the cosine of 30 degrees? Cosine 30 degrees, 0.8660, blah, blah, blah. But let's check root 3 over 2. It's the same. It's exactly the same. Now, I'm going to be careful. I don't say two numbers are exactly the same because the calculator told me so. I know otherwise that they're the same, but at least the calculator isn't trying to contradict me. Now, let me show you how else this is powerful. Let's go from 30 degrees over here on the right to 150 degrees over here on the left. Now we're at 150 degrees. Let's talk about 150 degrees. Just by taking the mirror image of this point, what do I learn? Well, the y-coordinate of this point has got to be the same as the y-coordinate of that point. They're the same height if I take the mirror image across the y-axis. So that means that the second coordinate, the y-coordinate, which is the sine of 150 must be 1/2. Let's try it out. Now I'm not even surprised. What about the cosine, though, of 150? 150 degrees over here. The cosine will be the same length as this length, but it's going in the negative direction. So the name of this point is back root 3 over 2, up 1/2. And back root 3 over 2 is negative root 3 over 2. Let's try cosine of 150. It is negative of root 3 over 2. Exactly what we had a second ago for root 3 over 2. Try to show that so that the light is not shining on the screen. Sorry. Okay. So again, when you think hypotenuse 1, what you get for the x leg is the cosine of that angle based on the x-axis. What you get for the sine, what you get for the y leg or the y-coordinate is the sine of that angle. Let's try it on the last famous triangle, which went 3, 6, 9, 12, 15. I think we checked last time that if I went over 15 boxes, I'll show you how to check this on your calculator, and went up 4 boxes, that was darn near 15 degrees. Let me show you how we'll check. This side is 4. This side is 15. This angle is theta. According to this picture, the tangent of theta is 4 over 15. But instead of wondering if I drew theta correctly, I could ask the calculator to undo this sentence with the tan inverse command. I could ask the calculator not the tangent of something equals 4 over 15, but I could ask the calculator, can you tell me the something whose tangent is 4 over 15? That's called tan inverse, which we'll talk about in a little while, not today. So on the calculator, It's on the tan button, but it's the blue thing above it. If I say tan inverse of 4/15, calculator say 14.93 degrees. That is darn close to 15 degrees. So that's why I said to you, if you wanted to draw something that looked honestly like 15 degrees, it's not exact, but just draw a 4/15 triangle. Now, when we drew that triangle, in our special triangles handout, we thought of that triangle as 4 on this side, √6 minus √2 on this side, and √6 plus √2 on this side. These are the exact measurements of that triangle. But now let's play our little game where we make the hypotenuse 1. If the hypotenuse becomes 1, then I have divided the hypotenuse by 4. And because these are similar triangles, all I have to do is divide the other two sides by 4. And that becomes the new horizontal side and the new vertical side. Sometimes when people are remembering this triangle, they forget which one should be plus and minus. But that's not so hard. You want the long side to be more than the short side. So the short side is going to be the minus version. Long side is going to be the plus version. This is 15 degrees. And now if someone asked me for the cosine of 15 degrees, I could just read this triangle. Of course, it's adjacent over hypotenuse. But the hypotenuse is 1. So dividing by 1 just leaves me with the adjacent side. So this is the cosine of 15 degrees. √6 plus √2/4. That is the exact answer. That is better in some ways than the calculator. Now, I do like the calculator's version. And I got to go back up here and find out what it was. Oh, I didn't show you that on the calculator. Maybe I should. I want to go look up that number, √6 plus √2/4. But it's way up here off the top of the screen. You can scroll up the screen and see the things you did previously. So √6 plus √2/4 is 0.9659 and goes on, but 4 digits rounded off is fair. In fact, I think if you're highlighting that number and you hit enter, it'll grab that number and put it on the command line. It'll grab that number down here. See how it grabbed that number and put it to your current line? So that's another way that's very handy to go get something you typed before and put it on your command line. Okay. So the cosine of 15 degrees is √6 plus √2/4. That is exact. That's what I really like to use when I'm doing calculations. But if I had to approximate, I could use the calculator to approximate. I'm sorry, I was off screen. Okay, one more thing about this, and then we'll launch into some new things today. I want you to think in radians too. I want you to think in portions of a circle. So what is 15 degrees in radians? There's a couple ways we can do this. Remember, 180 degrees is the same as pi radians. So you could multiply 15 degrees times pi over 180 degrees. And when you do that, and just by sheer luck, 15 goes into 180 12 times. Well, it's not luck, but why is it not luck, by the way? 90 degrees is half of pi. 45 degrees is 1/4 of pi. And 15 degrees is 1/3 of 45. So 15 degrees is 1/3 times pi over 4, pi over 12. There are 12 15-degree angles between 0 and pi. That's 6 right there. 7, 8, 9, 10, 11, 12. Now, I didn't draw that very neatly, but you can imagine the 12 thin pieces of pizza. So this is what I want to do on my calculator. I want to remind you that if someone gives you radians or requires that you use radians, you can do this on the calculator, no problem. You just have to know what 15 degrees is in radians, and then you have to tell your calculator to use radians. So back to calculator. Slide paper over. Let's go to mode. Let's go to degrees, radians, and change to radians. And now when I go back and ask the calculator, what's the cosine of pi? Pi is built into your calculator over on the right side, under the clear button, or if you like to say it this way, 5th row, 6th button, or 5th row, 5th button, second function pi over 12. And it's that same number again, because now the calculator is talking radians. Okay. So this is what I want you to absorb. That not only does the unit circle show you the sine and cosine of every angle by the point that the line intersects the circle, I also want you to absorb all these things now, that if you have a 30-degree triangle, sine and cosine on the right side, and you flip it over, now you get a 150-degree angle with the same sine and cosine, except the cosine portion is now negative because you've gone over to the other side. You've gone 180 minus theta. So this is one of our identities. The cosine of theta is the opposite of cosine of 180 degrees minus theta. The cosine of theta is the opposite of the theta on the other side. Now for sine, you notice that they're the same y coordinate. So the sine of 180 minus theta is always the same as the sine of theta. So these are two identities that we have on our sheet somewhere. I'm looking for them. I can't see them immediately. They're the supplementary angle identities. Okay. Let's do some more things with the unit circle. What happens, and I'm just going to pick out a couple problems from your book here in this section, and then we're going to move on to the next section. I'm looking in section 3.3 right now. And the thing that excited me about this book was in section 3.3, he gave you this picture. Now, I just slid this under my camera. It might be better if I pulled up the book on my screen, but just, you can look at this picture yourself in your book. It's on page 143. It's in section 3.3. And this is the exact same thing that we drew on Monday. This is the unit circle. And what he's trying to tell you here, he's trying to get you to memorize degrees and radians, 30 degrees, power 6, 60 degrees, power 3, 90 degrees, power 2. And he's also trying to plant in your mind that the name of that point, root 3 over 2, 1/2, is the cosine and the sine, cosine x coordinate, sine y coordinate of the angle. And the gravy, cherry on top, is if you take the 30-degree angle above the x-axis and the 30-degree angle below the x-axis, you automatically get the same sine and cosine, same x-coordinate, but the y-coordinate would be opposite. Here, the y-coordinate is plus 1/2. Here, the y-coordinate is minus 1/2. I just drew a red line in my book. Okay, not selling that puppy back. So unit circle is a very powerful way to bring together everything we've done. The famous triangles, the identities, some of the identities we've done, and the only thing he didn't do, now that I've committed, why don't I just go all the way, is he didn't add the 15-degree angle, which is pi over 12. And he didn't add the names of these points, which is root 6 plus root 2 over 4. And then I'm out of space, root 6 minus root 2 over 4. Now that's not unusual, and I'm not saying anything bad about the author or his book. Most people teaching trigonometry, writing a book about trigonometry, they only show you the 30, 60, 90, the 45, 45, 90, and the 60, 30, 90. They only show you the angles 30 degrees, 60 degrees, 45 degrees. They only show you two famous triangles. But this 15-degree triangle is worth remembering. And it fills in the gaps in the unit circle. And that's why I like to show you that triangle in my handouts. That's why I made this handout for you. Now, this handout also's got a pile of identities on it, right? And you could also use this as a formula sheet if you wanted to. It doesn't have every identity like the other sheet does, but I put on here what are some people consider the top identities, like cosine squared plus sine squared equals 1. And other ones on here you don't recognize yet. But these identities that I've placed on this handout, a lot of people call them the most powerful identities, the top identities. Okay, thank you for letting me know. I'll watch the paper there again. And at the bottom here, I put the 3 famous triangles. So now you have total control over the circle. So let me just throw an example on the board here. Let's look at a problem like 16. And I'll put my camera front on the screen. It says, why don't you calculate the sine of 7 pi over 4 negative and use the fact that sine is an odd function. So use, and I got to explain what odd function is. Use the fact that sine, I spelled the word out. That's not sine theta, that's S-I-N-E. Is an odd function. They don't mean strange function. To find sine of minus 7 pi over 4. Okay, let's think in our giant unit circle. And I'm not going to redraw the whole unit circle. I'm just going to try to draw this angle minus 7 pi over 4. I can think about what minus 7 pi over 4 is, right? This is 0, this is pi, this is 2 pi, which happens to be 8 pi over 4. So actually, this is very close to 2 pi, but I had to respect that it's in the negative direction. I'm going clockwise. So here's 1 pi over 4, backwards, 2 pi over 4 negative. I'll label them. 3 pi over 4 negative. Nice large pieces of pizza. 4 pi over 4 negative. But that's just equal to minus pi. Going clockwise is minus pi, going counterclockwise is pi. So I should be careful how I say equals pi. It actually equals minus pi. Minus 5 pi over 4. Minus 6 pi over 4. I must be getting close. Minus 7 pi over 4. Now let's find the sine of minus 7 pi over 4. And then I realize, well, think degrees or think radians, I don't mind. I say, oh goodness, the reference angle is just 45, 45, 90. I don't mind if you think in degrees and radians simultaneously. Let's be very careful about this angle. The angle is minus 7 pi over 4. So you were explicitly told to go clockwise 7 pi over 4. But the reference angle is 45, 45, 90. The reference angle is this pi over 4, pi over 4, pi over 2 triangle. And I know the sine and cosine of that angle. If the hypotenuse is 1, this is 1 over root 2. This side is 1 over root 2. And so the sine of this red angle matches the sine of this triangle. It is opposite over hypotenuse, which is 1 over root 2 divided by 1 should be 1 over root 2. Now, what does this mean about odd function? But first of all, before I explain what odd function means, I want to physically type that in and know for a fact that I'm right. Now, remember, I better be in radian mode because minus 7 pi over 4. And we did leave in radian mode. So always check what mode you're in. So let's type in sine of minus 7 pi divided by 4, stop. Oh, I got one too many parentheses there. I apologize. Let me delete that parentheses. Got it? So let's check it out. 0.7071. And you can file this away when you approximate, unless someone tells you to approximate otherwise. If you don't know how many digits to write down for trig function, and they didn't tell you otherwise, pretty safe to write down 4 digits, 4 significant digits. Rounded off properly, of course. This rounds off to 7.1. That's 0 right there. Is that the same as 1 divided by root 2? Absolutely. Exactly the same, at least for the first 10 digits, as far as the calculator is concerned. But it's actually exactly the same. Now let's talk about odd function. You may have used this word in a math class before, you may not have. But when someone says a function is odd, They mean that when you plug in the opposite of a number, you always get the opposite of what you would have got if you plugged in the number. This is the meaning of odd. Odd means when you plug in minus x, you get the opposite of plugging in x. It's also got a sister that is called even. When someone says they have an even function, it means when you plug in minus x, you get the same as plugging in x. So for example, cosine is an even function. You could check that out in many ways. Sine, according to this problem, they said sine is an odd function. I keep doing that with paper. Apologize. Let me move my book out of the way. So, how could I do the sine of minus 7 pi over 4 using this identity that sine is an odd function? So I could write sine of minus 7 pi over 4 apparently as minus sine of 7 pi over 4. Now where's 7 pi over 4? Minus 7 pi over 4 was to go all the way around except for one 45-degree 90 triangle. I guess, I'm trying to find a different color pen here. I guess 7 pi over 4 must be going all the way around, but stopping one pizza slice of pi over 4 short of a full circle. So minus pi over 4 and 7 pi over 4, what did we call those? Coterminal. Going minus pi over 4, you land at the same place as if you go 7 pi over 4. Now let's talk about 7 pi over 4. Again, same reference triangle, 45, 45, 90, right? And the horizontal side is an exact match to the triangle above. The horizontal side is 1 over root 2. This height and this height must be the same. But I am going downwards. So the name of this point is no longer 1 over root 2, 1 over root 2. 0.7 right, 0.7 up. It's now 1 over root 2 and down 1 over root 2. And the sine of 7 pi over 4, remember, on a unit circle, the point at the end of this radius 1, the point on the unit circle, is reading the sine and cosine to you. So the sine of 7 pi over 4 is negative 1 over root 2. But according to my instructions, to get the sine of minus 7 pi over 4, I take the opposite of the sine of 7 pi over 4. Sliding up, the two opposites have canceled each other, the opposite of the opposite, and you have just sine of minus 7 pi over 4 is 1 over root 2. So what he's trying to teach you in this problem is that there's a lot of ways to skin a sine or cosine. You can go clockwise, you can go counterclockwise. All that really counts is that you recognize the reference triangle. And if it's famous, you've memorized the sides. If it's not famous, I'll use a calculator. But you can identify every angle around a circle, whether you go clockwise or counterclockwise. You can identify every angle around the circle by using the reference triangle and shifting reference triangles to various places. How about minus 5 pi over 4? It's got the same 45, 45, 90 reference triangle. So its values are going to be 1 over root 2, 1 over root 2. But this time the x coordinate would be negative and the y coordinate would be positive. So this point would be 1 over root 2 negative and 1 over root 2 positive. That's the cosine of minus 5 pi over 4. It's the cosine of 90 degrees plus 45, which is 135 degrees. It's the cosine of 3 pi over 4. Because if I go clockwise, it's 1, 2, 3 pi over 4. It's the cosine of minus 225 degrees. Because if I go minus 180 and minus 45 more, I'm at minus 225. So he just wants you to be able to name angles, forwards, backwards, clockwise, counterclockwise, left side, right side, top side, bottom side. He wants you to be able to name sine and cosine using any quadrant and any triangle. I'll say one more thing before I get off of this page and launch the last thing we're going to do today. Remember, there are 6 trig functions. But tangent is sine theta divided by cosine theta, right? Cosecant is 1 over sine theta. Secant is 1 over cosine theta. And cotangent is the reciprocal of tangent, which would make it cosine theta over sine theta. So here's another powerful secret. If you know sine and cosine, of course you know all of them. Because sine over cosine is tangent. Cosine over sine is cotangent. 1 over cosine is secant. And 1 over sine is cosecant. You could use sine and cosine to do all 6 ratios. And so the fact that this point is cosine theta sine theta on the unit circle actually gives you all 6 functions. What's the tangent of 45 degrees? Well, it's sine over cosine. Sine is the y slot, cosine is the x slot. What's 1 over root 2 divided by 1 over root 2? 1. So the tangent of 45 degrees, or pi over 4, is 1. Check calculator, just to be happy. Go back to degree mode. Tangent, 45 degrees, 1. And don't be surprised. You knew it was going to be 1. You knew it was coming. You've been there before. Okay? Some of the touchdown celebrations are kind of clever. So and the soccer players do the same. And maybe football is football going away and is soccer becoming bigger? Well, everybody always predicts that soccer will take over the United States, but I think football is still larger. But soccer celebrations get weird too. So go Google strange soccer celebrations. I've seen some funny ones. So they're just having fun. You don't get to score too often, so let them have fun. Okay, now we're going to finish up what we're doing this week with kind of interesting application. And this is section 3.4. It's called arc length and sector area. Well, actually, the book calls it length of an arc and area of a sector, but I don't mind which way you say it. So I'm going to draw a circle again, and why not make it a pretty circle? So I'm going to get out my oatmeal box top. Actually, don't discount this when you're doing homework or a test or anything. You know, you want to draw a perfect circle. If you want a smaller one, get a soup can. But you can draw a perfect circle, just use a soup can or a can top of some size. Okay, so let me remind you of two famous formulas, and that is circumference. Circumference means all the way around. And the circumference of a circle, people use C, is 2 pi times its radius. So if someone tells you the radius of a circle is R, I love radius 1. I love the unit circle. But let's just talk about any generic circle now. Someone tells you the circle of radius is R, then when you go all the way around the circle, it's 2 pi times R. But what if you only went a part away around the circle? What if you only went halfway around the circle? Well, then you would take half of pi r, right? So this distance walking around half of the circle is pi times the radius. What if you only went a quarter of the way? Well, then you would divide by 4. What if you only went theta and you didn't be too particular about what theta was? Let's just say you walked or turned theta degrees, theta radians. Then how much of the circle are you walking right here? It's not the circumference of the circle. It's not even nearly the whole circle, but it is a part of the circle. And there's an easy way to calculate how long it is. This is called arc length. The S is called arc length. And when you have a theta and an R and an arc length, they're related by this formula. S equals R times theta. But when you do this, you cannot talk degrees. When you use this formula, theta must be in radians. So let's try it out. What if theta was 2 pi? Then I would have 2 pi r, which is the whole circle. What if theta was pi? I would have pi r, which is half the circumference of the circle. So this formula for arc length is just a way of expressing part of the circumference. But that's a really useful thing to know. Sometimes you don't want to know the whole circumference, you just want to know part of the circumference. Now, likewise, I'll show you one more famous formula that we might have time to do an example. You know that the area of a circle, famous formula, pi times r squared. That's what you call the area of a circle. So if r is 2, then the area is 4 pi. That's the amount of paint you need right here. Now remember, 4 pi is just a crazy number to you, but if you have to go and buy the paint, you can find out what 4 pi is. Sorry, 4 pi. Going to be about 12 and a half square feet, 12.6 square feet. So you walk into the paint store, that's the first thing that they ask you at Lowe's, Home Depot, et cetera. Say like, I need some primer. And they say to you, how much do you need? And you say, I need 4 pi square feet of primer. And then they kick you out of the store. They don't want to know 4 pi. They want to know an approximate number. So it's okay to say if the radius is 2, then the area is 4 pi. Yes, it is. But if someone wants to know what 4 pi represents, don't be obnoxious. Just tell them it's about 12.6. But what if I only wanted the area of part of a circle? And that's called, again, a sector. So the arc length is the portion of the circumference that you're walking. The area of this giant piece of pizza is called a sector. A section, but sector. And what's the area of a sector? It's not hard to remember if you remember the area of a circle. The area of a sector is 1/2 r squared theta. Now, if theta is 2 pi, then 1/2 times 2 pi becomes pi, and the area of the sector is the area of the circle. So if you forget this formula, remember this formula and what you did to the angle 2 pi. You cut it in half. But this is handy if you just want to know the area of part of a circle. But again, you got to be really careful. There is no mercy on this. Theta must be in radians. It won't help if you use degrees. But you know how to change degrees to radians. Okay, let me give you a simple example, and then let me give you a fun example. By simple, I mean a direct example, an ordinary example. And I'm going to pick this out right here. A lawn sprinkler is, I'll read it to you, but it's too small and I don't want to pull up the book on screen. Oh, what was that trick we used the other day? Is just put other books underneath it. Oh, sorry, didn't mean to hurt you. Okay, let's try again. A lawn sprinkler is, didn't mean to make you dizzy, located at the corner of a yard. The sprinkler is going to rotate through 90 degrees and shoot water out 60 feet. What is the area of the yard watered by the sprinkler? I'll reread it to you if we need it, but we can draw a basic picture here. Lawn sprinkler at the corner of a yard. It's set to shoot the whole 90 degrees right here. I guess 90 degrees, I usually put a little square, but 90 degrees. And it's set to project the water out 60 feet. There I'm using the hash mark for feet. Now, if I'm going to casually stretch a circle right here. What's the area of this quarter circle? I'm going to use this formula, 1/2 r squared theta. And the only thing I would get in trouble with is if I put 90 in for theta. That is not 90. That is what in radians? Pi over 2. So what area does that cover? 1/2 times 60 feet squared. That's the radius of this giant circle, times pi over 2. Now let's clean that up. I could use a calculator to clean it up too, but 3,600 times pi over 4. 2 times 2 on the bottom is 4. Then, since I'm already going after it, why don't I just divide 3,600 by 4? Give me 900. So let's type in 900 pi. I get this number of square feet. Now, if you're not brave enough to simplify things ahead of time, you don't want to take any chances, no problem. Just write 1 divided by 2. And then write 60 squared. And then write pi over 4. I don't mind which way you do that. Sometimes I type it in like this myself. Oh, and then I find out I'm totally wrong. Why am I totally wrong? I don't want pi over 4. I want pi over 2. So what am I going to do? I do not want to retype that. That would be a terrible waste of time. I'll just go up there and grab it and write pi over 2. Now it matches. What do math teachers say whenever they make a mistake that drives people nuts? Oh, I just did that to show you. I just did that to test you. No, I didn't. I just made a mistake. Just say you made a mistake. Okay, area 900 pi, but again, how much grass seed do you need today, Mr. Redmond? Oh, give me about 900 pi square feet. They would just kick me out of the lawn and garden center. I want about 3,000 square feet. Of course, we know it as 2827 square feet. Always add the units. But what would you buy? They'd also get angry at you if you asked for, oh, I need about 2827 square feet. Well, they say, well, we're just going to sell you this bag. And this bag for you, special customer, Mr. Redmond, it covers 10,000 square feet, but that's all we're going to do for you. Okay. At least I know how big that part of the yard is. Here is another crazy, crazy thing you could do. And that's how I'll wrap it up today. And you can go outside and test this. I want you to go and test this. Instead of thinking about this relatively large piece of pizza, an area, let's go back to the arc length formula. But let's use a tiny, tiny, tiny piece of pizza. And it's over here. And this relates to your homework problem that you're about to do. This is a very thin piece of pizza. You definitely don't want this. You'd feel cheated. But it's a part of a circle anyway. It's a piece of pizza. So what are we going to call this? Let's call this angle theta. But I can't even fit it inside there. So I'll just write theta outside. Let's call this radius, long radius, r. And let's call this piece of the circle S. It's the same as this picture. I'm just drawing a tiny, tiny theta, tiny, tiny s. Now, let me show you a really weird trick. This formula is still valid. Doesn't matter what the size of the theta is. And let me show you another trick. This is your thumb. It's about a ½ inch wide, 3/4 inch wide. But if you hold your thumb at arm's length in front of your face, the angle that it makes is very small. It's about 2 degrees. Now you can do this out on the street this afternoon or even around your house inside a room. Let's say that you see an SUV, and I'm specifically referring to your homework problem right now. Let's say you see somebody's Ford Bronco sitting down the street. And you hold up your thumb. And that Ford Bronco just, you hold up your thumb sideways. And that Ford Bronco is the height of your thumb, as far as you can tell, your thumb at arm's length. So what if that Ford Bronco, which you know to be about 6 feet tall, typical SUV is about 6 feet tall, just stand next to it. You know that that Ford Bronco is 6 feet tall, and you know that your thumb cuts out about 2-degree angle. If that Ford Bronco is 1 thumb in height, how far away is it? Let's check it out. The S right here is 6 feet. You know how tall the Ford Bronco is. The theta is 2 degrees, but that's not going to do. I'm going to have to turn it into radians. So 2 degrees times pi over 180 is pi over 90. And do you see what happens? If you know S and you know theta, then you can just divide S by theta to find R. So let's try it out. Ford Bronco, 6 feet tall. Theta, pi over 90. How far away, if that Ford Bronco is 1 thumb tall, how far away is the Ford Bronco? So I got to do 6 divided by pi divided by 90. You know, be careful with your fractions. Either put that fraction in parentheses, or how do you divide by fractions? Invert and multiply. I don't mind which way you do it, but make sure you enter it in your calculator correctly. Let me pull the calculator over here. Let me pull the paper over there. Let's try it out. What are we supposed to do? 6 times 90 divided by pi. That Ford Bronco is 172 feet away. Now, whether you do this out on the street this afternoon and just pace it off, you could pace it off. You know, what's your pace? Is your step about 3 feet? Well, go ahead and pace it off. You got a long tape measure, go ahead and do it. If you're in the garage and your basketball is on the other side of the garage and it's 1 thumb high, then how far away is your basketball? You have to know the diameter of the basketball. NBA basketball diameter, 9.5 inches, as I put in your homework problem. But you could do this. What happens if the house down the street is 2 thumbs tall? Well, then 2 thumbs is 4 degrees. And 4 degrees would be pi over 45. What this is called is something that a surveyor would call subtending. If you're a surveyor, then in your toolbox, you have a subtenths bar or similar equipment. You know, nowadays a lot of equipment is electronic. But a subtenths bar is just a little bar of metal that's got a certain known length, and they can hold it up against their equipment and say, I know this bar of metal is exactly 2 inches tall, but it's the tree down the street is the same height as this 2-inch tall bar of metal in my sight. How tall is the tree? This formula is a sneaky way to either find out how far away something is if you know how tall it is, or to find out how tall something is if you know how far away it is. You got to have one or the other. And the reason it works, so this is the last thing we'll say, is because if something is far away, he draws a nice picture in the book of an airplane. Now the airplane is a straight line, sure. And the arc of the circle S is a curved line. And I know that the straight line along the airplane is shorter than the curved line, right? But if this airplane is very, very far away, then the curved line that represents that arc S is very close to the length of that airplane. Now he's totally exaggerating this picture, so go find this picture in the book. Do you notice he says that angle there is 0.45 degrees? So, and look at his language. A 747 jumbo jet subtends an angle of 45 degrees. That means that it cuts out an angle of 0.45 degrees. Tiny. Your thumb is 2 degrees at arm's length, right? So this is 1/4 of your thumb at arm's length, even less. But if you're in a pinch, how far is that deer? I hold up my thumb. I figure that deer is about 6 feet tall. The deer is 1 thumb thick in my sight at the end of my arm. That deer is 172 feet away, according to what we just calculated. Now, I can't remember whether we talked about archery in this class or not. That's a kind of the goofy thing about being at home. We did not. So, you know, I have not. I like target shooting and archery. So just an ordinary recurve bow. If the deer was 172 feet away, then no, I don't think I would hit it with a recurve bow. And since I haven't hunted deer with bow, I wouldn't hit it at all because I'm not interested, but I don't have anything against it. Target shooting, archery, recurve bow, you're talking typically 20 to 40 yards, which is 60 feet to 120 feet possibly. I probably couldn't effectively take that deer at 172 feet. So I'll wait till the deer gets to be 2 thumbs close to me. And what would that be? That'd be about 86 feet. If that deer is 3 thumbs tall away from me, in my estimation, then that deer is about 60 feet away from me. That is well within the range of a recurve bow. So I don't, it's not often you get to say, oh, math is actually practical. I mean, I think it's practical all the time, but that's kind of a funny example. Okay, I talked too long. I apologize. I'm going to take these notes, but you can do your homework problem with what we just talked about. I'm going to take these notes and post them and get our video up, and you guys go outside and have a good day. Go try this thumb trick outside. See if it works. I'll see you next week.